Swayam Prabha. Digital India. Educated India.
Okay, welcome again, because we are here in basic surveying video lectures, and today we will be talking about again module number 2, and ours will be lecture number 3 in module number 2. The module is basic concepts of surveying. Well, we have already done module 1, we are in module 2. In module 2, we will be discussing many things today. However, before that, the things which we did in our last video lecture. In our last video lecture, what we did, we talked about some basic principles of surveying. This is very important. What are the basic principles of surveying? Well, it is what we will be discussing today is on chapter 3, or rather the lecture number 3. What we did in our last video lecture was very important, and let us recapitulate that. We talked about the basic principles of surveying. These are the principles which we should always keep in our mind whenever we are going for surveying, because these are very important points, and they control the kind of the work which you ultimately produce at the end of your job. Well, number 1 is the reconnaissance. What we did in our last video lecture, we started with an exercise in which we started, well, there is a little ground and we want to make a map of that ground. So what all steps are involved? The very first one was recce survey or reconnaissance. We go to the ground, observe it. This is a very important point in any surveying job. Then the second one, we decided, okay, we are going to survey this particular area by a particular method. In our last video lecture, we chose the method of triangulation. For this triangulation, we need some points in that area so that we can form the triangles. Now, why we are forming the triangles? Because we wanted to bring the skeleton of the area in our plotting sheet. So that idea is called working from whole to part, or establishing the control network. We want to establish first a very accurate control network, and we will be using that control network later on for our other surveys. So we don't work from part to whole, rather we work from whole to part. First we make the entire skeleton. We are not bothered about the details initially. What we are bothered about initially is the skeleton. It has to be accurate, and the details can be filled in later on. Then another thing, we must always go for the redundancy in the observations. The meaning is we should have multiple number of observations. Then we also talked about the check. We should have some observation which are not used in our general plotting work, but these observations we will use later on at the end of this final map. When the map is produced, when the final results are there with us, we want to check those results. So we should have something called a check. Then we are talking about plotting of the details. We can plot the details by various means. We saw that if 2 points are fixed, we know this length, so these 2 points are fixed, a third point is to be fixed. What we need to do in order to fix this point, either we measure both the lengths, or we measure both the angles, or we measure one length and one angle, or maybe one length and one angle this way, or maybe one more possibility, we drop a perpendicular from this point on this line. So here we know the distance here along the line, which we in our last lecture said x, and this particular distance perpendicular from the point, we set this as offset. So by measuring this perpendicular and this distance, we can plot this position or this point with reference to these 2 points. So we can plot our details that way. Then we are talking about very important thing, that is the plotting accuracy. Plotting accuracy, in our map, the minimum point or the minimum thickness of a point that we can make is generally, we take it as 0.25 mm. Okay, now what is the meaning of this? Within that 0.25 mm we cannot see anything, because it's a single point, a line, thickness of the line. We can't see any detail inside. Well, if that is the case, the corresponding distance in the ground, how do we find it? We find it by multiplying plotting accuracy by the scale. So we know the corresponding distance there in the ground. So the meaning is, because we cannot see anything within that point in our map, so we cannot plot any detail which is within that distance in the ground, the corresponding plotting accuracy distance. So we should always keep in mind, whenever you are deciding about your scale, okay, my scale of survey is this. So you know what kind of details, how accurate you should observe in the field. So plotting accuracy is an important thing. Then finally, we are talking about classification of surveys. How we classify? There were different classifications based on the instrument used, the area, the type of the area, the functionality, for what purpose we are using it. Okay, so there are different classifications. So this is all we discussed in our last lecture. Today, in our this video lecture, we will be talking about errors in measurement, and we will be looking into sources of error, classification of errors, systematic, random error, principle of adjustment, principle of reversal maybe, then basic terms, random error distribution, use of normal distribution curve and all that. Okay, so we are going to talk about errors in measurement. We said that in surveying, the measurements are the basic thing. We need to measure the things. So we need to also talk about the errors in measurement. What is the meaning of this? Let's start explaining this. This is a very important area, and we must know about this whenever we are doing the surveying. Well, let me give you an example. Here I have got a scale, and in this scale we have some graduations. Any length, for example, let us say I want to measure a length here using this scale. Okay, so what I will do, I will put this scale along this length and I say, okay, what is this length? So this is a procedure of taking the measurement. So we are taking an observation, we are measuring our length here. Now in measuring this length L, what do we measure? Are we measuring the actual value, the true value of the length? Now what is true value? True value is the value which is actually there. Are we able to really measure it with this scale? Now the answer of that is no. We cannot measure true value. Now why? One very simple answer of that. This scale has got a least count, and the least count of this scale is in millimeter. Okay, we can measure up to 1 millimeter, or we can estimate within a millimeter. We can approximate within a millimeter. Well, when we are approximating, how good we are in the approximation? Are we really measuring the true length then? No, because we are limited by the least count of the instrument. So never in practice we can measure the true value of any length, angle, or any geoinformation. So what we measure? We measure the true value, let us say we are writing it in capital for L, plus some error term, because we are introducing some error here. So this is the error term which we are introducing. I gave you just one example of the error, which is because of the least count. There may be many more sources of the errors. Well, let us start talking about those. What are the sources? The sources of error. Sources of error in measurement. Well, let us start talking them. Number one, are there any natural sources? Just think about that. Let's think about this scale only. Okay, this scale says that this is 1 meter, which is written over here. I can read from here to here, it says this is 1 meter. So when this scale was manufactured, when this length was given 1 meter, it was given at a certain temperature. Let us say the temperature at which this scale was given 1 meter was 27 degrees Celsius. And right now, when I am working in the field, the temperature here is not 27 degrees Celsius, rather more than that, 42 degrees Celsius. Now what happens? Because of this, if the material of this scale is such that it expands, all the material will, if it expands with the temperature, still I see it is written 1 meter here, isn't it? But because of the temperature, the actual length of this scale is not 1 meter, rather slightly more than 1 meter. Now if I measure any length with this scale which has expanded, our length measurement will not be accurate, rather we are introducing some error. So this is one example of natural source of error. There could be many more. I can give you one more example. For example, let us say many times you must have seen, as I am drawing here in the diagram, well, what I do, I suspend a heavy plumb bob. What this plumb bob is, here it is the thread or twine, and here is a heavy bob, okay, a very heavy material. We make use of this in order to find the direction of the gravity. Obviously, because of this weight, it will align in the direction of the gravity. So whenever we want to measure the direction of the gravity, we can make use of this simple device. We want to ensure whether a particular wall is vertical or not. You must have seen many masons using this plumb bob to ensure the verticality. Now, how nature is coming into the picture? If there is some wind is blowing, okay, it's not appreciable, but the wind is blowing there. Because of the wind blowing, what will happen? A constant force will be acting on the plumb bob, and the plumb bob will be now slightly displaced. I am doing slightly exaggerated one. It will not be this big, but it will be slightly swayed from its vertical position. So what we are able to do, we are not able to measure the exact perpendicular or for the vertical direction, the direction of the gravity. Rather we are measuring something else. So again the nature is playing a role here. So whenever we take the measurements, we have sources of errors which are because of the nature. Then the second one, the second source of the error are because of the instrument. Well, how? How come? I gave you one example that in this scale, if the least count, there is a limitation of the least count. Let us say the least count in this case is 1 centimeter. In one case, in other case the least count is 1 millimeter. Okay. Now can you start thinking? The limitation, in this case we can measure more precisely, more closely, while in this case our measurements will not be that close. So what is happening? Because of the instrument itself, there are some errors being introduced. I will give you one more example. Well, this says 1 meter. Is it so? The question is it really 1 meter? Because this has been manufactured by someone. Someone has manufactured an instrument which may be the scale, the simple one like this, or maybe a sophisticated instrument. And the instrument says this is 1 meter, but is it really so? That's the big question. So if it is not really so, it says it is 1 meter, but actually if you measure it with some standard, you find it is 1.01 meter. So we have some error included in our instrument, and whatever the length we will measure with this ruler. So what we are doing, the actual length of this is 1.01 meter, but we are considering this to be 1 meter. The meaning is, if they are in the ground, let us say this length, if this length is 1.01 meter, okay, and if we are measuring it with this scale which has actual length of 1.01 meter, then this length, which is actually 1.01 meter, will be shown as 1 meter, isn't it? Because our scale is showing 1.01 meter as 1 meter. So this is one source of error which is coming because of the instrument. Well, the third one you can guess very well. What is the third source of error? It is because of the person or personal errors, the person who is working there. Well, I don't want, I'm a bit tired, I'm not happy today, and I'm taking the measurements. The weather is not very good, it's very hot, so I'm not very happy about working. So what I do, I start committing the mistakes when I take the measurements. Also, when we take the observations over a scale, where our eye should be? Our eye should be exactly over the graduation or exactly over the mark for which we want to measure the length, and then we see the graduation corresponding to that. Well, one source of error could be if I displace my eye here or here, the parallax. So what is happening now? The person who is working with the instrument is introducing some error. So there are errors because of the person also. Well, having seen all these types of the errors, what we will do now, we will go into another classification which we say classification of error. So far we are talking about the sources of the errors. Now we will see classification of errors. What are their types? What I will do, I will start with one example. Let us say in number 1 case, because the number 1 type of the error we say to be blunder or mistake. Well, the example in this case is, let us say this is the target. Many of you must have done the firing in your NCC classes or somewhere. So in your firing, what you try to do, you have a little bull's eye here. Your aim is to fire at the point here in the bull's eye. Okay? Well, if you are careless, careless means you are not even targeting the bull's eye. What you might end up firing your bullets somewhere here or outside or very much outside, isn't it? So what you are doing, actually the person who is taking the observation, he is committing some mistakes. There are some blunders. So that kind of thing we say the blunder. Now how it can happen if I am measuring this length? Well, I measure this length, I find this is to be 30, actually the length there in the ground is 30.7 centimeter. Okay, well, I record it, I say, well, I have observed it 30.7. Now when I write this length in my notebook, length measurement number 1, I write it as not 30, 13.7. It might happen. It does happen, because whenever you are working in the field, if the conditions to work in the field are not very, very good, which is normally so, because you do the survey out there in the ground, the conditions are not very favorable always. So your mind is a bit tired. So you end up writing a length which is 30.7, which you also measured as 13.7. So what you are doing actually, you are introducing an error, which is we say blunder or mistake. Okay. Well, the second classification of the error, the second one of this, we say systematic error. Systematic error. Now what happens in this case? The same example of the target here. Well, the bullseye, you are trying to fire here. Let us say you are not aware about the gravity. You are a very good fireman, but you do not know that the gravity exists. So what you are doing, you are trying to target at the center but because of the gravity all your bullets are coming here down. Okay, maybe a little one will go there, but most of the bullets will be coming here. Is it or not? So what is happening now? See, the gravity is playing its role. So a systematic force in the nature is bringing your bullets down, and your bullets are firing here, not at the target. So this is a systematic force which is working. So the error is, we say, systematic error. Similarly, for example, let's say we are measuring with this scale, and we know this scale was made at a temperature of 27 degrees Celsius, while the temperature now is 41 degrees Celsius while I am using it. So obviously this scale has some expansion in its length. So what is happening? In all the measurements, let us say I use this scale to measure this length, and I keep this scale once, twice, thrice, 4 times, and so on. So what I am doing? I am introducing some error always, everywhere. So this kind of error, for which you saw it in the case of the gravity, in the case of the temperature, for which you can write a mathematical model, or we can say those errors which follow some physical law, as in the case of the temperature. There will be many cases where you can write a mathematical model for the error, because it follows some physical law, so you can eliminate that error. So those errors we say systematic error. Well, the number 3, this is very interesting error now, and we say this error to be random error in our observations. For example, let us say, again I am going back to our target. You are trying to fire at the bull's eye, which is this point. Your aim is to fire at the center here. Okay. Well, what we do, we ensure there is no blunder, no mistake. Your firing instructor is very strict. He is ensuring that there is no mistake or no blunder. You are not firing here and there. At the same time, you are also aware that the gravity is there. So what you are doing, you are taking some precaution and you are raising your gun a little bit, so that instead of firing at this point, you fire somewhere here, so that you are taking care of the gravity also. Now if this is the case, what will happen? All your measurements, all your bullets will now fire like this. Okay, maybe some are farther also, but most of them will be nearer. Now this is a very interesting observation, very interesting observation. What we see here, these bullets are spread throughout my bull's eye, while more number of them are concentrated in the bull's eye and less are in the outer periphery. Now one thing, why we could not fire in the bull's eye exactly? Can we? No, still there are many sources of errors which you do not know. You are breathing, some little turbulence in the air, some little problem with the gun, some little problem with the bullet itself. It does not go in the straight path. So there are many sources of errors which you cannot account for, and these are the sources of the errors which may go in positive direction or in negative direction. We do not know how they are varying. So that kind of error, those sources of error, they contribute the error which is called random error. Okay, so what we observe here, the random errors, their distribution is, number 1 point about them, they are equally distributed in positive and negative direction. What is the meaning? Over here, there are random errors in all the directions. It is not that they are in only one direction, they are in all the directions. So their probability of occurring in positive direction and negative direction is same. Well, the example here with the ruler, the scale. while I am measuring this length, I am trying to keep my scale exactly over the points here and here. What is the guarantee I am keeping exactly over it? Again, there is some subjectivity involved. The human judgment is involved. I may be keeping it slightly here or slightly here. So that introduces the random error. So what will happen? The error amount, now number 2, point number 2 about it. What we see here, random error which are large in magnitude, for example this, occur very less. There is less possibility of the random errors which are large in amount of occurring. But the random error which is small, for example here we have a huge concentration, the chances of their occurring are more. So we can say large random errors, they occur less, while small random errors, they occur more. Okay, we will see in a moment some further things about this random error. But this is one error. You know, if you eliminate from your observation, let us say your observation is L, for a length which you measured it as L. You eliminate that this is not blunder or mistake, fine. Then you eliminate some systematic error SE from your observation. You know the model, how this error has occurred. So you eliminate the systematic error also. Now in your observation, whatever the outcome of this, for example, let us say the outcome is L dash, is still this L dash is not equal to true length, because your L dash has still some errors, and those are the errors which we say random errors. So we can say the random errors are those errors which remain in observation even after eliminating systematic errors from the observation. Okay. Now what we will do, we will discuss two more terms here. One term is called precision. What is the meaning of that? Again I am going back to our example of target. That is the bullseye. You are trying to target the bullseye somewhere here, okay, but you are not able to do that. Precision means, let us say, when you are trying to target here, there are some systematic errors also working, and because of the systematic errors, most of your observations, or we can say the bullets, are clubbed in this area. It might happen. Let us say some force is working there upward now, okay, not like the gravity, and most of your observations are now in this area. Well, this is one case. This is a person A fired these bullets. Person B also fires these bullets, and for person B, what he gets all his bullets, let us say like this. Well, what would you like to say about person A and person B? Who is better firer? Who is a better fireman? Who has got better aim? Despite there is some systematic error, which is maybe your barrel is slightly tilted. Though you are targeting the bullseye, all your bullets are being fired here, slightly swayed. But this person has all his bullets very close to each other, okay, while this person has his bullets in a wide spread. So definitely we can say person B is more precise in his firing, okay, than person A. So this explains the term precision. We mean by precision the closeness of observations. How close your observations are. Another example, well, in this scale, if the least count of this scale is 1 centimeter, you are trying to measure up to 1 centimeter, and then you are approximating within 1 centimeter. That is case number 1. In case number 2, the least count is 1 millimeter. So now you are confident to measure up to the millimeter, and you are estimating only within 1 millimeter. Obviously, in this case the precision is more. Okay, then compared to the other case. Another term which is related with the precision is accuracy. Well, what is accuracy? Let's go back to again our target, the bullseye here. You are trying to fire at the center. Now, in one case you fire here. Let us say the fireman A, he fires here. In the second case, there is another fireman and he fires here. Now, out of A and B, who is more accurate? What is the meaning of accuracy? Obviously, you will say B is more accurate because he is firing nearer to the target, near to the bullseye, while A is not that accurate. Now, in terms of precision, both A and B are same. The precision, the spread is same, but A is not accurate. So, what is the meaning of accuracy? The meaning of accuracy is closeness of your observations to the true value. How close your observations are to the true value? Well, there may be a very interesting case. In that case, in this bull's eye, now there are two persons. One person has got his bullets here, the other person has got his bullets here. If you take the mean of these, the mean is here somewhere, that is for observer A, and for the second person B, the mean will be somewhere here. Even if the precision is more in this case, it is not accurate. Here the precision is less, your observations are far apart, but the accuracy is more. Okay? But if you eliminate the systematic error from your observations, if the systematic error is eliminated, then what will happen? All these bullets, they will come to the target or the bullseye. So, if the systematic errors are eliminated, in that case, the precision of the observations become an indicator of the accuracy. Now, what we will do, we will look at one more important principle here, that is called principle of adjustment. Now, we know by this time, whatever we are measuring, for example, let us say there is a triangle, and for this triangle we are measuring three angles, theta 1, theta 2 and theta 3. There are 3 points there in the ground, okay, one point, another point, another point, and using some equipment, some instrument, I stand at point 1, number 1, I measure the theta 1. Similarly, I measure theta 2, theta 3, all the angles. Now, we know that this theta 2, for example, it is not really the true value. The true value in this case is theta 2 hat, let us say this is the true value, but theta 2 is not the true value. Why? Because theta 2 has got some errors in it. We have discussed this thing that we cannot measure the true value. So, all our theta 2 has got the error. Now, if that is the case, well, because this is a triangle, I can write now as sigma theta hat, the true angles between these 3 points should sum to 180. Obviously, the true angles, if we can measure true angles, sigma, the theta hat, they should sum to 180 degrees. But if you are writing sigma theta, the observation, will it be equal to 180? No, because all our observations have got some error also. Well, there in the field, there are 3 points for which we have measured these angles. The angles have got the error, but the field doesn't. The angles which I have measured have got the error. So, what I need to do? I need to correct my angles so that they satisfy the condition of the field. The condition of the field is that these 3 angles which I have observed should sum to 180. So, what I need to do? I need to apply some correction to my angles, and we do it by the procedure of adjustment. We will see in detail about this adjustment later on. So, now we will talk something more about the error, some more terms. Well, the very first term that we would like to see is true error. We have already seen the term true value. We cannot measure the true value. There are limitations, so many errors coming into the observation. So, we cannot measure the true value. Well, so do we know the true error then? If I know the true value, then only I will know the true error. Because the true error, for example, let us say there is a length, its true value is capital L, what I observe is small l. So, the error, if I write error as E, and the true error will be L minus L. But I do not know L. If I do not know L, just by using the observation, I can't find the true error. Well, what we can find? We can find, I am going to give you another term that is called relative error. Well, in some cases, for example, here in the case of the scale, I know what kind of error is being introduced because of the least count. I know that thing. Let us say that error which is being introduced because of the least count is delta L. Now, if I observe a length of line which is here L1, I can find delta L by L1, and this we say as the relative error. Now, why do we need it? We need it because using the same scale, I can also measure a length which is L2. So, in that case, the relative error will become delta L by L2. So, we can compare our observations, compare the error. So, this is how this relative error is used. Many times, this is also called percentage error, where you simply multiply this by 100 and that becomes the percentage error. Okay. Now, we will talk about one very important concept, that is called most probable value or MPV. We do not know true value. Yes, we do not know that. What is most probable value? It is a kind of replacement for the true value which we use mostly in our cases. The most probable value is defined as one which has maximum likelihood to be nearest to the true value. Well, let us explain this. A value which has maximum probability of being nearest to the true value, because we cannot get the true value by any means, but what we can do, we can go nearer to the true value. I will give you one example here. Let us say there is a length L. L is the true value which we cannot measure. What we are doing, we are observing this. In one case L1, L2, L3, we have taken 3 observations. In another case, we are taking from L1 to L100, 100 observations of the same length. more redundancy here in this case, less redundancy. Now by taking the mean, arithmetic mean of these, I will get an L bar of case number 1. I will get here also an L bar of case number 2. There are two cases. So obviously, just by common sense right now, you can say that the probability of L2 being nearer to the true value is more. So we can say this is our most probable value, or rather the other way around. Out of all these 100 measurements, which measurement is most probable? Is it L1, L2, L3, L100? We do not know about it, but once we have the observation, which is the mean, we can say this L2 has the maximum probability of being nearer to the true value. So this L2 is our most probable value. So what we are saying in this case? We are saying that the most probable value is the arithmetic mean. This is how we take it mostly. If I write the most probable value for some observation as x bar, so the meaning of that is it is sigma xi by n, where I varies from 1 to n. For anything, any quantity, any variable, there are n number of observations x1, x2, x3, which we are writing xi here, and that is the arithmetic mean. And we are saying that the arithmetic mean is the most probable value. Is it really so? Can you prove it? Now to prove it, we will do a little exercise. And I will define one more term before in that. Let the term is residual. I write the residual as R, and this is written as x bar minus x for any observation I. Okay. So what is the residual? Residual is the mean of the observation, or sorry, x bar we are taking as most probable value. Let the x bar is most probable value, which has maximum chances being nearest to the true value. If that is so, in the case of the x bar, we define the residual as the most probable value minus the observation. So for all the observations I is equal to 1 to n, we can find their corresponding residual. So this is called the residual. Now we will make use of this in order to prove that the most probable value is nothing but arithmetic mean of the observation. So we had written that our Ri, or the residual, was x bar minus xi. What I do, I sum it up for all the observations. Let us say sigma Ri for I is equal to 1 to n will be sigma x bar minus sigma xi, I is equal to 1 to n. Well, now look at this part. This is very important. The residual, what will be the sign of residual? We are talking here now only in the case when all our observation, okay, our variable has only random errors. Let's be clear about it. Whatever we are talking here, our variable, our observation has only the random error in it. We have already eliminated the blunders. We have taken care of the systematic error from the observations, and our observations have got only the random error. Okay, we are talking in that case, and only in that case we are saying that the most probable value will be the arithmetic mean, and this is what we are going to prove. And only in that case we are defining the residual, which is the most probable value minus the observation. Well, once that is clear, we are looking into this part. What this part will be now? for a large n many observations. You know what is the sign of R, the residual? The R may be in positive direction as well as in negative direction, which we saw. The random errors have got equal probability of going into the positive direction as well as in the negative direction. This is what we have seen already. So the sign of R will be positive and negative with equal probability. If that is so, for large n, this particular part will be equal to 0. If that is so, what we can write now? Sigma R I sigma x bar minus sigma x I. What we can write if this becomes 0? We can write it as sigma x bar is sigma x I. What is sigma x bar? Sigma x bar is n times the x bar is being summed up. Okay, so that is equal to sigma x I. So the x bar, the most probable value, comes out to be sigma x I divided by n, and this is nothing but the arithmetic mean. So what we proved? We proved that if our observations have only random error, in that case the most probable value of the observation is arithmetic mean. Well, having said that, now we will see another important thing, that is random error distribution. We have already seen some of the things, but we would like to see it in detail now, how the random errors are actually distributed. And in doing that, for any set of observations, for example, let us say this is an variable or an length which we need to measure. We measure it xi, I is 1 to n, and we find the most probable value, which is the arithmetic mean. Also we can find one more term, that is called sigma, that is the standard deviation, which you find by x bar minus xi sigma of that divided by n minus 1 and square here. That is called the standard deviation. What does the standard deviation show you? The standard deviation shows you the spread of the point. Okay, we'll talk about this standard deviation also later on in detail, how we will make use of this. Well, the random errors, the way we are talking about them, they are actually distributed in a particular way. Here it is our variable x, and this particular value is x bar here, while here it is from positive infinity to minus infinity. Now this curve, what does this show? We will talk about it. This is basically called normal curve. Also it is called Gaussian curve. Many times it is called bell shaped curve because it has a shape of a bell. Now what is the meaning of this? We saw earlier also that our random errors, how they are distributed. Just think of the example of our firing of bullet, how those were distributed. If I do it again here, you are trying to target here, but you end up firing somewhere here also, but more observations in this area, more as you go nearer. This is how the bullets were there. This is how the random error is distributed, and the same thing is seen here in this curve. There is equal probability of an observation going below your most probable value on this side, that means the error is negative, or on the positive side the error is positive, because the most probable value is the one which is nearest to the true value. Any error which is negative into that will take its value towards negative side or the less than the most probable value, and any error which adds to it with a positive sign will take the value of the variable towards the positive side. So, what we see, our observations or our error is equally distributed in both positive and negative side. The chances of getting negative error and positive error are same. Now, here in this curve, this is our variable, while this is the probability of occurrence of any variable. For example, if a variable is here x1, so what is the probability of occurrence of x1? The probability of occurrence of x1 is this value. The probability of occurrence of your most probable value x bar is maximum. Obviously, there is also a probability of occurring an error which will be infinite in size on negative side as well as on positive side, but its probability will be very less. Okay. So, this is how the curve is. Those errors which are large in magnitude, for example here, because these errors are large in magnitude, so their probability, they are small in magnitude and their probability of occurrence is very high, while the errors which are large in magnitude on this side, on this part, their probability of occurrence is less. So, this is how actually the random error is distributed. So, what we will see, we will look further on this distribution of the random error. I am going to draw the same error distribution or the normal curve again. From minus infinite to plus infinite, and thus our x bar, the most probable value, and the distribution, the probability density function of this is given as fx, which is 1 by sigma under root 2 pi e exponential raised to power minus half into x bar minus x. X is an observation and or variable, while x bar is the most probable value, divided by sigma square. This is the probability. Fx or the y gives the probability of occurrence of a variable x. Okay. So, this is the equation for this curve. Now, what we can do? We can draw the same curve for the error also. Okay, this will not touch here, this is asymptotic here, they will not meet. Plus infinite, minus infinite, and in the case of the error, we will have 0 error here because it is the most probable value, and the negative values of the errors and positive values of the error. And the error will be also distributed in the similar way, in the way the normal distribution is. And in most of the observations in surveying, unless the observations are biased because of some systematic error component, we will have all our errors generally distributed in this form. So, what we saw today, we saw about the errors in the observation, errors in the measurement, and this is a very important concept. We should know about these errors, because in surveying you go to the field, you measure something there. So, you should know what kind of errors may creep in. These errors, they come because of the nature, because of the instrument, because of you, the person. Then second thing, we talked about the types of the errors. There could be mistakes, there could be the systematic errors. We can eliminate those systematic errors provided we know the mathematical model or the physical law which they follow. We can also do corrections for all the systematic errors. Then after eliminating all these errors, still our observations are not free of the error. We have another kind of error there, which is random error. So, we saw today a lot about the random error, what it is, how it is distributed. It is distributed in a Gaussian way or the normal curve. We saw the characteristic of this, that the positive error and the negative error have got equal likelihood of occurring. Smaller errors have got more probability of occurring, while the large errors have got less. So, this is what we have seen. What we will do in our next lecture, we will try to make use of these concepts, and we will try to take the normal curve, standard normal curve, and we will try to make use of that, so that we understand that what we have measured, how we represent it, how we present it, how confident we are about a particular measurement. Well, thank you very much.